before we look at how we grow things in the soil, how we look after the soil, how we improve the soil, it's useful to look at where soil comes from, how it's made, what it's made of. The study of soil science can be incredibly involved and involves a lot of chemistry, but I think there are a number of things that are quite simple to understand about soil which really helps, and actually reducing soil just to a chemical discussion about how it functions misses some of the most important points. So, where does soil come from? 25,000 years ago was the peak of the last ice age. 10,000 years ago, the ice sheets retreated from the UK. Now, 10,000 years ago isn't long. 10,000 years is about when we think agriculture may have started in the Middle East. 5,000 years ago is the beginning of recorded history. So 10,000 years ago, what is that? 40, 50,000 generations of people? Not long. So that's at that time the UK had little or no soil, just rocks and sediments, including silts and clays. So how did the soil get here? So what happens is that rocks and sediments are colonised initially by things like lichens, then mosses, and then as the little bits of debris get washed into cracks, things like grasses come along, and then eventually other bigger plants and shrubs, and then trees. So what we see here is the same sort of landscape, obviously a bit more hilly, but a few years later, good few years later, and this is the process known as primary succession, the process whereby plants and biological action turn rocks and sediments into soil. And here you'll see the soil is building up in the folds of the land, and this soil is actually created by those biological processes. So the take home here is that soil is created by life. Ecologically, this process is known as succession, where a community of plants and its associated life change the environmental situation, change the situation in which they are living. So primary succession is going from bare open ground or sediments to a eventual more stable state. So as we talked about before, we've got bare rocks initially colonised by lichens, and then small annual plants, lichens, then grasses and herbs, and then shrubs and pioneer trees, and then eventually here we have what's described as a climax community, a more stable community, not a completely stable community, of usually longer lived perennials, and in this case a woodland of longer lived trees. You can think of that in the UK as oaks, and actually the small leafed lime or the ash and elm trees on the downs. In permaculture, we talk about succession, and one of the permaculture principles, in fact, is the use of succession, the understanding of succession, and the acceleration of succession to build up soil fertility or move a situation from one place to another in a desired and beneficial way. But we can talk about that more later. But the use of succession and how plants change their environment and their associated life is very much part of how we manage the soil to improve its fertility. But we'll come back to that. So vegetation that behaves in a natural way builds soil. The vegetation captures the energy from the sunshine and uses it to make organic matter, and that in turn feeds a soil food web of bacteria, fungi, worms, invertebrates, and then the larger animals. They are what makes soil. We'll come to what soil is, of course, later, but they are part of the soil, this living food web. Whether that's happening beneath grassland or beneath woodland, which are probably the two main types of vegetation on the land in the world, vaguely similar processes are going on. The diagram at the bottom shows how you can get different soil above the same basic material. So calcareous loess is a sediment, and yet we have different types of soil built on top of it, controlled by the vegetation growing at the surface level. So on the left we've got trees, and on the right we've got prairie or grassland. So you get a completely different soil in these two different environments. Why is that? Well, underneath woodlands, forests that tend to stay damp, you tend to get a fungally dominated soil, and that breaks down organic matter, dead things that hit the ground, eventually completely. Whereas under grassland, you get because it dries out periodically, you tend to get bacterially dominated soils, soil ecologies, and they break down the organic matter into long chains of humus, not humus, that's a Middle Eastern dip, humus. I nearly tongue-tied myself there. So we get these completely different types of soil. So under the grassland you've got a deep topsoil which stores a lot of fertility. In the forest, interestingly, most of the fertility is in living material, and the rainforest, such as the Amazon, is a very good example of that. If you cut down and remove the forest, you remove 90% of the fertility. It's growing in little more than sand. Whereas if you remove the vegetation on a piece of grassland, if it doesn't wash or blow away, there's still a lot of fertility there to grow things on. So, what is soil made of? This diagram shows a typical, and I must stress typical, soil composition. It's an example. It's not to say that all soils are like this. There is a great deal of variation. In this example, getting on for half of the soil is made up of minerals, and half is made up of air and water. And there's a jagged line between those two because the proportions of each vary as the soil dries out or gets wetter. And I should say, to be pedantic, we should talk about gases in the soil rather than air, because as you go down into the soil, it's not air in the same sort of composition as we have above the ground. This example has 5% organic matter. A few soils have much more than that, like the peats of the uplands and the fens, and a lot of soils actually have a lot less than that. Now a more detailed look at the organic matter, and again, this is just an example. This has a 80% of that 5% organic matter is the humus, and that is dead organic matter that is rotted down. 10% is roots, and 10% living organisms, worms, beetles, etc., etc. In fact, in some soils, much higher percentage of that is going to be particularly the roots element. So I should have said in the last slide, the organic matter was abbreviated as OM, and it is that organic matter in the soil which is the fundamental driver of life. It's created by life, and it gives us life, and what turns what would otherwise be a heap of air, water and mineral particles into the wonderful living thing that soil is. And without that we would be dead, because we have nothing to eat, and the plants would not live on the soil that they've created. So organic matter, abbreviated as OM, that's the reason why lots of religions in the world chant OM, because of the importance of organic matter, honestly. Moving on now to consider soil structure, and that is to do with how soil particles are stuck together and the spaces between them. So we're moving on from just this idea, which some people have, that soil is just this heap of crumbs of chemicals, and to begin to think of it having an actual structure, and going back to its composition, obviously how tightly it's packed together and what spaces there are between the soil particles is to do with how much air and water get into the soils. So two diagrams here of soil, or photographs in fact. One described as poor structure, one described as good structure. This is in relation to soil health and the ability to grow plants. So the soil with poor structure has a lack of roots in it. It has dense areas of soil that are tightly packed together and few spaces between it, few pores. Whereas the soil with good structure is described as granular. The bits of soil are sticking together but leaving spaces between them, and there are bigger gaps on between them, deeper into the soil, and the roots are going down deeper. So not only is the life in the soil changing the soil chemistry, but it's also changing its structure, because what creates that good structure is the roots growing down into the soil and dying back and rotting back, and the worms going through it, and the action of bacteria and fungi on the soil. And the absence of life leads to soils becoming dense and the air and the water not being able to get down into them. So there's the irony that a dense soil on a heavy rainy day will allow all the water to run off the surface rather than getting draining into it, whereas one with a good structure will allow the water to drain in. And this is how we use soil, what we do with it in modern agriculture. Large areas of monoculture, large areas of ploughed up land. So the moldboard plough as it's called, top right, is extensively used throughout the world to turn soil over. And we've begun to talk about the important ecology of the soil, where each individual thing has its niche. So treating soil by removing the life from it, killing most things in it, the plants at least, by turning it over and moving the worms from where they had built their home underneath the ground to on the surface, and the bacteria that fungi that live on the surface underneath causes a lot of problems. Unfortunately, this also affects the structure of the soil, and you can see in the bottom right, I hope you can see that the raindrop, that's one raindrop that's hit some wet ground, and you can see the small particles of soil within it. So if rain falls on bare soil, it's very prone to erosion as it splashes the soil back up with the particles and flows away. Typically, we plough or dig the surface of the soil to make the soil lighter and more aerated, to make it easier to grow things in. But one of the consequences of that is at the point at which we stop digging, we create not always, but in a lot of soils, a hard and impenetrable layer known as a pan, a hard pan, a plough pan, which is indicated with these blue arrows here. So you'll see that the loosened topsoil above it is little more than a spade's depth, and then you get into ground which is quite difficult for roots to penetrate into, difficult for the worms, and that really can create a barrier to plant growth. This is a diagram of actually prairie plants, North American prairie plants. The scale on the left hand side is in feet, so we've gone back into old money, but you'll see that the plants are reaching less than a metre above the ground in growth, and yet their roots are reaching about 2 metres deep, which is about the depth of the soil in the prairies. And in doing so, they're keeping the soils open. They're opening up those pore spaces, and interestingly, when those plants die back, they effectively inject compost deep into the soil. And this is obviously a schematic drawing rather than an accurate one, but typically the biomass, the weight of the living material, is twice or more beneath the ground what it is above the ground. So this is a very important part of this soil functioning is for soil ecology. So what about cultivated plants? Well, this is a corn plant, a sweet corn plant, and in a good soil you'll see that this one is reaching down more than 7 feet, getting on for 8 feet down. So plants will reach much deeper down if they're growing in a soil with good structure. This is really important in terms of thinking about plants' ability to access nutrients, but also critically to withstand drought and get moisture in drier periods. If you've got a very shallow soil, it dries out quickly and you're much more likely to need to water your plants or for them to fail or do poorly if you don't. So what can we do about a hard pan? Well, it is worth it if we can to break it up rather than wait for nature to do it for us, because nature will do it, but it will take a long time. So if we're trying to rehabilitate an area of garden or an area of farmland, it is worth breaking it up if we can. So the commonly available implement for the job is a fork, probably a metal garden fork, which is strong enough usually to get into the hard pan, but it doesn't go deep enough, so you'd probably have to double dig to get down there. So not all that helpful. I mean, dig off the top layer in order to break up the pan beneath it. The tool on the right is very hard to buy and very hard to find, which is sad and shows how little valued it is. I don't even have a name for it, but the tines, the spikes on it, you can't really see from the picture, are longer than in the garden fork, and having two handles and that flat bar, you can jump on the flat bar and pull on the handles to rock back. So both of these, the idea of breaking up a hard pan with both these tools is not to turn it over, it's just to get into it and just loosen and lift it. So with the one on the right, you jump on it, you lean backwards, and that lifts it up. I have actually used one, it is pretty effective. On a farm scale, this can be done with bigger scale pieces of equipment. This is referred to as keyline plough, this particular one, which you'll find mentioned in permaculture texts. You can get, they're probably a bit more effective, but you can get more commonly available things called subsoilers in the UK, which do a similar thing. They have long tines which get down into the ground deeper than the hard pan and break it up. They should only be used in dry weather because the action of the machinery can do more harm than good otherwise. Moving on to soil texture now. That is, as the name implies, to do with how it feels, and it's to do with the relative amounts of different sizes of mineral particles in the soil. This shows the different particle sizes of the mineral proportion of the soil, which is to do with that texture. So from clay, which is so small particle size that they're tiny, and in fact they chemically tend to stick together, through to sands, gravels and pebbles, granules of larger particle sizes. In fact, we're usually just talking from sands to clay in terms of soil texture here. So a coarse sand can be up to 2 millimeters across. So in terms of soil texture, we talk about three particle sizes: sand, silt and clay. That's all soils are made up of, or all mineral soils, nearly all soils are made up of. So this diagram is quite tricky to get your head round. So we have at the top, the very top, we've got 100% clay. At the very bottom left, we've got 100% sand. And at the very bottom right, we've got 100% silt. And all the other positions in between it are a mixture of the two. But it's easy to read it wrongly and think you've got it all adds up to more than 100%. So if you do actually read it correctly, and that's in the same direction as the numbers are, you read parallel to the numbers. So you'll see the numbers down the right hand side and across the bottom are at an angle, and it's the one that the line that they're lined up with that you need to follow through. So if you look right in the middle, you see the clay loam, and just beneath that the loam. So you might think of a loam as 40% silt, 40% sand and 20% clay. And that is probably what the RHS would anyway describe as the perfect soil. And it is the perfect soil, I guess. But sometimes reading old gardening books, you might be tempted to think you've got to move to somewhere with loam or give up gardening. And all soils have got their own advantages and disadvantages, and can be done. You just have to do different things with them to care for them, and they're better for growing one thing or another. So what I would suggest you do, if you haven't got your head around this diagram immediately, is you pause the video here, perhaps grab a cuppa and have a good look at it and see if you can get your head around it. We will look at it more in the session, but it is incredibly difficult for people to, most people anyway, to get their heads around at first. One of the ways you can work out the relative proportion of these different particle sizes, Stefan will look at other ways of telling the relative proportion of the different mineral particle sizes, the texture of the soil, using hand texturing methods with you. So what about the properties of different soils? So here we have different columns for sand, silt and clay, and a sandy soil is described as light, whereas a clay soil is described as heavy. It literally is heavier because of the amount of moisture it holds. Obviously a sandy soil feels gritty, a silty soil feels smooth, and a clay soil feels sticky. This is beginning to look at how you tell them apart a little more. A sandy soil might roll to be a crumbly sausage if you're lucky. A silty soil will roll to a sausage the size of your little finger, and a clay soil will roll to half or a third of the size of your little finger. But what about these characteristics and what do they mean to us? So a sandy soil does not hold on to water and nutrients well, so that is obviously an issue. Whereas a clay soil will hold on to water and nutrients very effectively. Whereas a sandy soil is crumbly and aerated, a clay soil can be sticky and airless. And in terms of compaction, the sandy soil is pretty much impossible to compact, whereas a clay soil is very easily compacted. And so this is a lot to say about how we manage clay soils. They've got a lot going for us in terms of water holding and nutrients, but they're so easily damaged, they so easily become compacted and airless, that the plant roots can't get down into them, and once that's happened, like we discussed with the hard pan earlier, it's very hard for it to get it back. So we really do need to be careful about how we manage them, not digging them too much or taking machinery across them or walking across them in wet weather. So the good news is that Om is the answer to everything, and so adding organic matter to sandy soils definitely helps to improve their nutrient holding abilities and hold on to water. Organic matter also helps in a clay soil, but less important for holding on to the nutrients, but more important for holding on to the structure, to improve the structure rather than holding on to the structure, and allows access to those roots and the drainage and the air into the soil. Temperature too, rock heats up quickly, sandy soils tend to heat up quicker, whereas clay soils tend to heat up more slowly. So a clay soil can be quite difficult to germinate seeds in the spring, if you're wanting seeds to germinate early in the season. Whereas a sandy soil might be much better. Whereas if there's something you don't want it to break its winter dormancy too early, it might be better in a heavy clay soil. So soil texture also affects soil structure. So here's some more of the diagrams we looked at earlier. The three across the top are poor structure, and the three across the bottom are good structure. On the left we have top and bottom is the same soil texture. It's all clay soil. The middle one is the same soil texture. It's all the sandy clay loam. And the right hand two are both sandy loam. So if you look at them, the ones with poor structure and the ones with good structure look quite different from each other. And yet look across the bottom, that all the soils with good structure, despite being of different texture, are look more similar. They have lots of pore spaces and they're granular, and that is the action of biological life on the soil, and that is what we need to enhance through our management of the soil. We need to keep life in the soil. We need to keep plants growing in the soil. We need to keep worms going through the soil, beetles, etc. And that will look after our soil and give it that good structure that we need, regardless of its texture. So that was a look at where soil comes from, what it's made of, its structure and its texture. And I suggest now you may want to have a look at the work that Stefan's set you on observing soils and the soil texturing. There's another presentation from me on soil fertility and how it relates to growing plants, and also more on living soil as well.